Diana Aga grew up in the Philippines, near a pristine river where her family swam and fished for food. As the population increased, the river became so polluted that it turned black.
It's actually devastating.
Preventing future environmental degradation is what drives Aga, a SUNY Distinguished Professor and the Henry M. Woodburn Professor of Chemistry at the University at Buffalo. Aga studies, among other things, PFAS compounds, also known as forever chemicals. These chemicals are manufactured for countless commercial products. They have subsequently been found in water, air, soil, wildlife, even inside our bodies. More alarming, PFAS have been linked to cancer, reproductive issues, and other serious health concerns. This has prompted regulatory action in Europe and the US. It has also prompted Aga, a worldwide expert in chemical and environmental pollution, to develop ways to detect and potentially destroy PFAS compounds. Welcome to Driven to Discover, a University at Buffalo podcast that explores what inspires today's innovators. My name is Cory Nealon, and I will be your host for episode 4, Forever Chemicals. Professor Aga, thank you for being here. Can you tell us a little bit about your childhood and how that connects with the work you do now?
Yeah, so I was born in the Philippines. I was raised in a very small village. I remember having no electricity, no industry around. So we grew up playing games like hide and seek and swimming in the river, making playhouses made of banana leaves and coconut leaves and bamboo sticks.
And so that pristine sort of idyllic childhood that you're describing in a sort of a pristine environment, that has since changed. It's changed over the years. Can you tell us about that?
Now you can find McDonald's, you can find Starbucks, you can find all these industries and business establishment that I see here in the US. So, and there's a lot of people now.
Can you swim and fish from that river now?
No, I wouldn't do that anymore. It's literally black now, and sometimes there are trash floating, plastics floating, and some, food packaging floating. So no, I wouldn't swim anymore.
From your childhood, your experiences growing up, how does that inspire what you do now?
It's the basis of why I have become an environmental chemist. When I was in college, so I went to Metro Manila, where it is even more polluted. In the beginning, I was actually doing forest products engineering because we have a lot of trees and I wanted to do something in the engineering side because I like math. But then when I went back home, I see all this pollution and I thought I should really do something to help clean up the environment. Naively, I was not even thinking about chemistry. I was thinking something else, like engineering to remove waste. But then I got really interested in chemistry and I started seeing things that explain almost everything that we observe every day. So I became a chemist. And then I learned that there's so many branches of chemistry that you can do. You can be an organic chemist where you make all the chemicals that end up sometimes being a pollutant. Or you can become an environmental chemist where you can think about how to determine what's in the environment and how to remove them and work with engineers. So I didn't need to be an engineer. I can work with engineers.
And like many people from the Philippines pursuing academia, you come to the United States. Where did you end up when you arrived here?
Oh, it's an interesting story. I did my PhD at the University of Kansas. And that's because back then, we didn't have all the internet and all this easy way of finding out about a place. So I just look at the book. I look at the United States map and I saw Kansas is in the middle. And I thought, if I go in the middle of the US, I could go anywhere to the East Coast, to the West Coast, to South, to North in a day. Because Philippines is so small, you can do that. But then I realized that US is a huge place that actually when I was in Kansas, I never left Kansas until on my 4th year. But it turned out to be a very good education.
Your research covers a lot of ground, everything from industrial and agricultural pollution to pharmaceuticals and antibiotic resistance. But today we're here to discuss PFAS. Can you tell us what PFAS chemicals are and why they're known as forever chemicals?
Yes, so PFAS, PFAS, right? PFAS stands for perfluoroalkyl and polyfluoroalkyl substances. So that's a tongue twister. That's why we just call it PFAS. And it's also easier to say forever chemicals because they exist in the environment for a very, very long time, to the point that some of these PFAS actually do not degrade at all. And it's very hard to determine how long each of them or many of them will be in the environment.
So they don't ever break down?
Okay, so I want to clarify what never breakdown means, right? So the most well-known PFAS are the PFOA and then the PFOS, PFOS. When people talk about PFAS, those are the two chemicals that they measure. Those two chemicals, I don't even know that we know about their half-life or how they degrade because I don't think they do. So PFOA and PFOS are now banned. We no longer use them in products. They have been replaced by what we call GenX. So GenX actually degrade, but when we call degrade, they just break into two pieces where oxygen is. So now you have two chemicals that are also PFAS.
Two as opposed to one, making things potentially more complicated as far as what is out in the environment.
Yes, and what is really interesting in this GenX is that it's shorter chain and it breaks into even a shorter chain. It becomes more water soluble, that it is harder to remove from our drinking water. So it's actually more problematic in terms of drinking water.
I've read that firefighting foam is one of the most prominent sources of PFAS. What other commercial products contain these forever chemicals?
They can be in pizza boxes. So because PFAS are really good in repelling both water and oil. Normally, it's one or the other. But PFAS have this special property, so you can use them in pizza boxes so that the grease from the pizza doesn't go soak into the cardboard. It's also in food packaging, like in microwavable popcorn. It's also in our cookware, those non-stick pots and pans. They contain PFAS. Now, in our more personal products, like the toilet paper contains PFAS. Some eyeliners contain PFAS. Clothings that have stain resistant have PFAS. So it's almost in every products you can think of.
These chemicals make their way into the environment. Can you tell us where in the environment PFAS have been found?
Yeah, so I guess everywhere. So the first times they've been found are in surface water, of course, because that's where when we throw our garbage or flush our toilet, they all go to the sewage. And so they've been found in wastewater treatment plants, the incoming and effluent also, because some of them are not removed. And then they end up in surface water. And then in surface water, there's the fish and wildlife. And so now you find them in fish and birds and even in bird eggs because it gets transferred from the birds that eat the fish. So now the bird lay eggs and it's also in the eggs. And now we are also finding them in the rain. Believe it or not, the concentrations of PFAS in rain is actually higher than in drinking water.
And with PFAS migrating into the environment, how can this be harmful to human or wildlife's health?
Because PFAS are both water-loving and fat-loving, it accumulates in our fat. So when we consume products that is contaminated by PFAS, whether it's drinking water or whether we're eating food from a pizza box or food that had been cooked in pots that has PFAS, then we accumulate some of these amounts. Even if our daily intake is really low, it accumulates in our blood. It accumulates with our proteins. So over time, when the concentration is high enough, it will affect our metabolism. So pregnant women who have high contamination in their blood with PFAS may transfer the PFAS into their offspring through fetus and then also through breast milk.
And the transfer of these chemicals, it's been known to cause, or I should say it's been linked to serious disease, correct?
Yes. Many different diseases, in fact, from type 2 diabetes to neurodevelopmental delays to cognitive behaviors, learning behaviors. So there are many effects that have been linked to PFAS in addition to cancer.
PFAS chemicals have existed in some form or another since the 1940s. Why is it now that we're just sort of having this collective awareness and concern about them?
It's the availability of advanced analytical techniques. We have this ability now to really detect small amounts of chemicals in all kinds of samples. It used to be very difficult to analyze PFAS. So they've been there. We just didn't know it. It's been in our water. It's been in our food. We just didn't know it. So in the last few years, I think it was actually in the 1980s when people had been able to detect them in blood. And that's when we realized, maybe we should look into these fluorinated chemicals, because fluorinated chemicals are all man-made. There is no naturally occurring organic chemical that has fluorine in it. So it has to be man-made. And that's when people were aware. However, it was only shown to be present in blood, but there were no evidence that it affects people mentally, cancer-wise, or health-wise. It's only more recently that a lot of this knowledge had come about. And that's why now, worldwide, there's an increased awareness of the health effects of PFAS.
You direct the University at Buffalo Renew Institute, which studies all sorts of issues related to the environment, energy, water. What is Renew doing right now to help solve this problem?
Renew is an institute that you can think about it as a think tank. My mission is also to catalyze interactions between the faculty to advance research in many areas in environment, energy, and water. And just specifically in PFAS, which is a passion of mine, we have so many expertise that may come up with a potential solution on treatment, on analysis, on understanding the impacts on humans and wildlife, and on coming up with new materials that may potentially replace PFAS.
And one of the projects the Institute is working on, it involves potentially, for lack of a better word, destroying PFAS that are out in the environment. Could you elaborate on that?
Yeah, so I actually have 3 grants just on PFAS. The first grant is developing techniques to analyze PFAS, because as I mentioned earlier, these are very difficult to analyze. I also have a project funded by the EPA, Environmental Protection Agency, and that's to study toxicity of PFAS mixtures. Because right now, when people study toxicity, we look at them individually. So compound A, compound B, compound C. But in reality, all these PFAS exist as mixtures in the environment, and we have no way of measuring how they impact when they are in mixtures. The third project I have is with the NIH, National Institute of Health, and this is in collaboration with the engineering department, where we're looking for materials that can break down PFAS. We know that some of these nanomaterials partially degrade PFAS, but do not degrade them completely. So we're going to combine these nanomaterials with microorganisms that will do the job, finish the job. We're looking for microorganisms from soil, from water, from contaminated areas that we can isolate and grow in the lab and figure out which of these thousands of microorganisms have the capability to biodegrade PFAS that had been partially broken down by nanomaterials. And hopefully we can degrade them completely.
So those microorganisms would consume the broken down PFAS, like eat them in a sense?
Yes. So right now there are only very few bacteria that are capable of degrading PFAS. The original PFAS have all the carbons with fluorine. Carbon-fluorine bond is one of the strongest bond, and that's why bacteria cannot biodegrade them. However, there are some bacteria that if you just start removing just one fluorine, the bacteria can start chopping them up, can start eating them up. But you gotta do the job of removing 1 or 2 fluorine first before the bacteria can consume them.
Sounds incredibly complex and challenging.
Yes, and we can also now, so the other thing is, if we know what enzymes in the bacteria are doing this, we can engineer the bacteria so that they can produce some of these enzymes. So it's, of course, these are all done now in the lab. So putting them in the environment is something else. But we have to start from the lab to understand, to even figure out if we can do this. And we can do it because there are now ways to engineer bacteria.
So it seems like there's some room for optimism here.
Oh, definitely. I would like to think so. All the research going on just in our university and in many other universities and in many countries as well. I think in the near future, we should find a substitute. We should find a solution to remove PFAS from many of our products, from our drinking water, from our food. So I am very optimistic that it will come.
Well, that's great to hear. Thank you for being here.
Thank you for having me. It's been a pleasure.